three operations, gradient, curl, and divergence, play a basic role in the applications of vector analysis or vector calculus. We already know that the gradient of a scalar function, gradient f, or write as nabla f, that is partial f partial xi plus partial f partial yj plus partial f partial ck, or write it on coordinates form, that is partial f partial x partial f partial y partial f partial z. This is gradient. Gradient is all operation. Gradient operates on scalar function. Now we define two other operations, curl and divergence. Curl operates on vector field. Curl vector field f. If f is p x y z I plus q x y z j and plus y r x y z k, then the curl f is defined as partial r partial y minus partial q partial z I plus partial p partial z minus partial r partial x j plus partial q partial x minus partial p partial y k. It's difficult to memorize this definition, so we use another form of the curl. Okay, so the third one, if we divergence. The divergence is easier to memorize. Divergence f, that is partial p partial x plus partial q partial y plus partial r partial z. This is easier to memorize, but for curl it's difficult to memorize the definition. So we use an operator called the nabla operator. Or nabla, the nabla operator or del operator. The nabla operator is defined as I partial x plus j partial y and plus k partial z. It's defined, use this one. So the divergence, also first the gradient. Gradient f, that is nabla f. And the divergence f, that is nabla dot f, and cur f, that is nabla cross f. Cross f we can write as that is I, j, k as partial x, partial y, partial z. That's p, q, r. It's easier to memorize the curve. Gradient f, that is partial f, partial xi as partial f, partial y. We can write actually we can write as partial x, partial y, partial z. Then operator on f, that is partial f, partial x, partial f, partial y, partial f, partial z. Or the nabla operator always can also write as coordinates. So the divergence, that is partial x, partial y, partial z dot p, q, r, that is partial p, partial x plus partial q, partial y plus partial r, partial z. But for the nabla operator, we cannot this write like an inner product, but it's not inner product because we cannot exchange the f and the nabla operator. We should note that's different. The nabla dot f does not equal f dot nabla. That's different. The nabla dot f, that is partial p, partial x plus partial q, partial y plus partial r, partial z. But f dot nabla, that is p, partial x plus q, partial y plus r, partial z. That's different. So they are not equal. That's the operator nabla and the two definition and the two operations, curl and divergence. Let's to do some calculations. If f equals xzi plus xyzj minus y squared k, find curl f and divergence f. This is capital F. The solution is the curl f, that is nabla cross f. We can use the determinant and partial x, partial y, partial z, and that's p is xz, q is xyz, and r is negative y squared. So for I, that is negative 2y minus xy I. That's actually, we can write in details. That is partial y negative y square minus partial z. That's x y z and I. G, that is partial x. That's x y z minus partial y. That's x z. That's G. For K, that is partial x y z. Right in the second row. That's for K. That is partial x y z minus partial y. That's x z. That's K. So that's equals negative 2y minus x z. That's I minus that's y z minus 0. That's J. That's plus y z minus 0. That's K. So that is negative 2y minus x z I minus y z J plus y z K. That's the curve. Yes. X, Y, Z. For G, oh sorry, for G, that is partial x. Here is, sorry, that's negative y square. Partial Z. That's partial Z. Okay, so he is not right. For that is negative x. So there's something wrong. So the first one is negative 2y minus xz I plus xg plus yzk. Now that's the answer, the right answer. For divergence f, that's partial x xz plus partial y x y z plus partial z, that is negative y squared, that is z plus xz. That's the divergence. Divergence is much easier to compute. Take the derivative for the first one in terms of x, the second in terms of y, and the third one in terms of z. That's the divergence and curl. Compute the divergence and curl. And some properties of curl and divergence. The first one is the curl gradient f that equals 0, and the second one, that is the divergence curl f is 0. The first properties we can write as nabla cross nabla f that equals 0. Or write the second one can write as nabla dot nabla cross f that equals 0. This is two very important properties for divergence and curl, and some other properties we can write or we just omitted. These two properties are most important properties for the curl and divergence. The proof is directly. The proof is directly. We just compute the curl gradient f. That is I, j, k as partial x, partial y, partial z. That's partial f, partial x, partial f, partial y, partial f, partial z. So that's 0. By the the equivalent of mixed partial derivative. And the second that divergence curl f, that is partial x, that's partial r, partial y minus partial q, partial partial q, partial z, partial q, partial z, plus partial y, that is partial p, partial x minus partial r, partial that's partial y, partial r, partial that's partial p, partial that's partial r, partial x, partial p, partial z. That's partial p, partial z. That's partial r, partial x, plus partial z. That's partial p, partial q, partial x. That's partial q, partial x minus partial p, partial y. Let's actually use expand or bracket that equals 0. As you did directly. So from these properties, we have a theorem, conservative vector fields. There's a theorem. The theorem states that if F is a vector field on simply connected region, we call D, and or its components have a continuous first derivative, then f is conservative if and only if its curl equals 0. Its curl equals 0. Okay, that's the theorem. This theorem is actually from the properties. The curl gradient is 0. If f equals curl, then f is the gradient of f, then its curl equals 0. The curl equals 0 can the proof is actually from f equals gradient f, then it's equal 0. That's by the previous the properties. If gradient f or the curl of f equals 0, that is partial r. We know that the partial r partial x minus partial q partial y equals 0, and partial r partial y minus partial p partial z equals 0. That's c partial. Sorry. By the definition of the curl. By the definition, partial r, partial y, partial q, partial z equals 0, and partial r, partial x, partial p, partial z equals 0, and partial q, partial x minus partial p, partial y equals 0. So f is conservative. For in the space of for the space vector field, for the plane vector field, we can view that r equals 0. If r equals 0, that is plane vector field. As plane vector field. If for plane vector field the curl of f is just a partial q, partial x minus partial p, partial y. K. For plane, actually, for plane vector field, gradient the curl of f, that is partial q, partial x minus partial p, partial y times k. So that's for the plane curve, and any other operations can treat f as a space vector field, just let r equal 0.